Yeah, we'll start. Uh, yeah, this session is going to be probably one of the heavy sessions. It's not easy. My basic question in the morning, which I had with myself, was should you learn transformers? No, I'm just asking you. Do you think it's worthwhile? Because it's not easy. I mean, it's not easy in the sense it's a pretty involved code. It's not a cakewalk code. It's not just 5 lines, 10 lines. It runs into pretty long area. Now I'm going to start. Hopefully we will make headway by 4:30. If by 4:30 we are able to understand most of it, or some of you are able to understand most of it, we have made good progress. Now, what is a transformer? Heart of everything. Whatever you are seeing around you which is happening in Gen AI is happening because of the transformer. We went through it last time. I gave an overview of what a transformer is going to be. At the basic level, there are various definitions of transformer. One is you ask a question, it generates output, answer to that question, which is what you see ChatGPT doing most of the time. That is what we call an encoder-only architecture, because you ask a question, it is able to understand that question and able to generate an output. It's a next token business, also called, and I think I explained this term last time, called autoregressive. That is, it generates one word, then the next word, then the next word, and so on. That is one kind of transformer. There is another kind of transformer which takes a whole bunch of English and it doesn't answer anything. On the contrary, it summarizes it, which says, it takes a ton of text and says, this is what it means. So basically that is another kind of transformer. Again, a kind of encoder. Then there is encoder-decoder architecture, which is the old classic transformer, the way it was first introduced. There's an encoder portion and a decoder portion. The use case of such a transformer is what? Basically translation, where you take a sentence in English, translate into Spanish, or translate into French, or anything to anything. Basically, it's a language translator. So that is an encoder-decoder architecture. It needs an encoder also, and it needs a decoder also. So that is another architecture which will go around. And then nowadays, of course, we are not going to cover it today, but the granddaddy of all this, not granddaddy, the most important threat today, which will revolutionize where Salesforce, all these companies are now working towards, is agentic workflows, that is LLMs built with ability to act, which we call agentic transformers or agentic workflows. To understand them, it is always better to understand the transformer at the core level where we are going today. Agentic workflow is today the cutting edge of LLM technology. And what can it do? It can understand simple rules in spoken English or any language. Instead of translating them into another language or summarizing them or generating the next token or giving an answer, it actually does action. And it does smart action based on what it understands of what is told to it, what it realizes, senses it, and it's able to convert it into an action. And that is the holy grail, because that actually is where LLM technology today stands at its zenith, as of today. Obviously, the last word is not set. There are many more things coming. One of the major areas we are working with and we are getting heavily invested in is the domain of drug discovery, where we take details about various drugs, various diseases, understand how to design drugs. So we're creating a whole group of about 30-40 people from the second year students now, because you guys are too old now for that, because I need 1.5 years with them. So that is again a movement we are starting of, because this domain is also very rich. This is not just drug discovery, but many different domains. There is supply chain and logistics, and a massive implementation of LLMs. Then there is the whole thing of legal technology, where we are saying, why do you need to go to a lawyer to generate a brief? You have a problem, you will have a lawyer who is a ChatGPT based or LLM based tool. You tell the problem, he'll pull up all the case law, create a brief which you can directly file in the court, or maybe just use the lawyer to file it. So that's all happening. But you know what? Unless you understand, if you want to actually do something in this space, you need to understand at its core what a transformer does. Last time I tried and explained how it works briefly. Today what we are going to do is we are going to understand it in much more depth at the code level, and understand it at the code level and take it forward. So we are going to understand the encoder, and if time permits and your mental capacity permits, we will go to the decoder. But at least the basics of multi-headed attention, embedding, positional encoding, and basically how the stack looks like. If you are able to get it across, then even if I'm able to do that, then I can take the decoder in the next session. Or if you're smart, we can take the decoder today itself. Okay, so the transformer architecture, I think most of you would know. You should have got this document. Of course, you can see it here, but you can see it on your laptop too. I don't know, whichever works for you. Just tell me whether you have got it or not. Okay, so if you have got it, just open it. It's maybe much easier to see it there than us having to struggle with it on the screen. Let's go piecemeal. You have this picture with you, yes? So we start right at the bottom. What is the first layer? And then we'll try and trace it to the code, okay? No, I'll not do that. I'll go through the encoder first and show you the entire encoder code at one shot. I'll just summarize the encoder, which I did last time. So, can you go a little below? So the inputs. Look at the left side. You have the inputs. Now you will say, what are the inputs? Inputs is any sentence. For the time being, let's think that the sentence is in English. It can be in anything. So I give a sentence which may be a question to the ChatGPT or to the LLM, or which may be a command to the LLM, could be whatever. So I have an English statement. Then there is an first processing that we do is the embedding. Now what is embedding? Basically, embedding consists of two parts. Anybody? What are the two parts in embedding? One is tokenization and the second is embedding. So let me explain in one line or two lines. Tokenization is what? Breaking up, chopping that line into words into tokens. Last time I talked about every word need not be mapped to one token only. Quite often a word gets mapped to more than one token. So there may be two tokens. Sometimes there may be three also, but rare. So we take the tokens, we chop them into tokens, and then we embed the tokens. Embedding means what? Converting the tokens into another set of embedded tokens. They are also called tokens. Difference being that now after embedding, we get tokens to a form like this. I'll just say this. If you say king, token for king, subtract man from it, add woman to it, you'll get queen. So it is brought to that level. I hope you understood, right? So that is called embedding. That is converting the token. Token is just a number which marks a thing in the vocabulary. When you embed it, it becomes a vector. We start looking at it as a vector, a n-dimensional vector. And why do I call it vector? Because if you take the n dimensions together, they represent something significant about the word, which is not just the word itself, but the semantics of the word. You will agree with me, because unless you have semantics, you will not be able to say king minus man plus woman is equal to queen. Unless the semantics is embedded in that vector, just simply subtracting vectors and adding vectors will not get you to from king to queen, correct? So that is called embedding. And how does it perform? It's basically you get a built-in tokenizer which chops them and embeds them. So we'll come to the code in a minute after I have gone through this journey, one flow. So that is embedding. So once you go to embedding, now if you see after embeddings, what have we done? We have converted every word in the sentence into more than one or more vectors. We have captured the meaning of the word, but in a sentence, words come together. We have not captured the position of that word in that sentence. That is called positional encoding. That means every word or every token must be added some value which does two things. Now listen here carefully. Every word is word by itself. So far what does it have? It has only the meaning of the word, or let's say the semantics of the word. It is not influenced yet by where is this word in that sentence. That it has not borrowed. Now what happens is, there is some effort to capture where this word is in this sentence, starting from position 0 to position n being the size of the word, size of the sentence. Somehow that position where it is occurring is encoded into that word, which so far only had the semantics of the word. Now, when we encode position, there are two parts to it. One is called, how do you encode absolute position, and how do you encode relative position? These are two different challenges. What is absolute encoding, position encoding? Is this word the first word? Is it the second word, third word, fourth word? That is called just absolute positional encoding. Are you with me? Is it first, second, third, whatever? If you capture that and add it to this word, somewhere we have captured the position, where it is occurring. Relative positioning means how two words are apart from each other. How are they close to each other, or are they away from each other? Do their encodings reflect whether these words are close to each other or away from each other? So the positional encoding logic which this foundation paper proposes has a mechanism to capture both the absolute position as well as the relative position. That is, I am two words away from that word, that is relative. I am at position 4, absolute. Both the sense has to be captured, and the functions which we will soon see and I will talk about will demonstrate that we are capable of capturing both position absolute and position relative. So, and I must pause here and say, this area of positional encoding, what was proposed here, has obviously undergone substantial change. For example, Llama 2, Llama 3 uses a completely different positional encoding, and different LLMs which we see in the market have played a lot with positional encoding. In fact, a lot of seminal papers have been created on positional encoding. If you're interested, maybe one day we can explore what are the different algorithms which are in vogue today for positional encoding, because this world is changing very rapidly. So we have the positional encoding. At this stage, what do we have? We have basically encoded the embedding of the word, the meaning of the word, the semantic of the word, and also the position of the word in the sentence, because you are taking the whole sentence as a whole. So you have to take both. So we have captured both. How we'll do it in Python? Hold on, just 2 minutes. Now once we do that, then the vectors or the sequence of vectors that we have now hits the main block, which we call the encoder block. Can we see that whole thing? Yeah. So now if you see the encoder block, it has two portions. There is a MHA block and there is a FF block. Okay. MHA stands for multi-headed attention. FF stands for feed forward. Okay. I remember I had talked about why do you need both of these people. Okay. I'll illustrate again. Then we'll talk a little bit about their implementation and then proceed. I need the attention block basically for what? Basically to find out how one word is related to other words. We are not talking about positions now. We are talking about their meaning, their purport. How this word is connected to the rest of the words. So that is the flow of attention from the other words into this word and from this word into other words. So to enable that, we have what is called as the multi-headed attention block. Now you will say, attention to a certain extent I have understood is a question of transferring knowledge from the other words into this word, and we'll talk about the mechanism it happens. I think I briefly alluded to last time also. For every word there are three vectors which we generate. The famous Q, K and V. The query vector, query matrix otherwise, the key matrix and the value matrix. So conceptually, whenever I want something from the other words, I raise a query on them. I say, I am so and so, I want to know about you. So this is my query. I ask the other word uses its key matrix to tell, or key vector, to tell how similar that word is to me, and if similarity matches, that portion or that fraction of my value gets transferred to the first word which raised the query. I'll repeat this again. One word, if you look at one word's perspective, that one word will ask all the other words, I am so and so, that's my query. Each word will have its query, key and value. So this guy's query will be compared with this guy's key, and if the query and the key are similar to each other, we say we are matching. So lot of your value I can adopt. Lot of your value means lot of your information will apply to me. If we are two apart, obviously your information is irrelevant to me. So that is what passes attention. That is called the attention mechanism, or what we call traditionally as self-attention mechanism. That happens. We talked about it to length last time. Besides attention, there is another thing which is at play. Now, before we go forward, there is, why is it called multi-headed attention? Often, including the original architecture, which is this architecture, we split that vector. Remember, when we are saying vectors, we are talking about the whole word. So, the representation of that word. Now you think with me. When we say query key value, I may be querying from one perspective. I may be querying from the perspective of, for example, I may be interested in the femininity or masculinity of the other words. That is what I am interested in. And if they match, maybe transfer of value has to happen. Or I am connecting between the pronoun and the proper noun. And if the proper noun connects with the pronoun, I hope you understand grammar. You know what is a pronoun? So, that could be another perspective. One is, I said, gender. I am of this gender, I am a word of this gender, you are a word of the same gender, whatever applies to you may apply to me. So that is one kind of similarity. Another kind of similarity would be, I am a noun to your pronoun, so whatever applies to you comes from me. Yes? Yes, sir. I am a verb to your noun, means whatever I am saying about you. So by having this kind of a correlation, now if you see, already we are talking of three perspectives. Whether I am a verb to you, whether I am a noun to your pronoun, am I matching you in gender? We are looking at already three different perspectives. So the designers of this architecture believed that when we say query, key and value, when we talk about similarities, these similarities have to be taken under 3 or n different lenses. Don't take only one perspective. Have the ability to have multiple perspectives. And multiple perspectives means multiple queries, multiple keys, multiple values. If you visualize that and try to think about it, these are different ways of looking at that word. Sometimes it will look from its gender of that word, sometimes from the grammar word, sometimes this word applies in which location. So different kinds of context will give different kinds of meaning. And this kind of information, if you are seeking, you need not a single attention mechanism, you need to split the attention mechanism into multiple heads, each head looking at one perspective. I always give at this stage the example of Ravan. I should speak. If you look at Dashanan, they captured it very well. Each head, do you know, they were not just 10 heads. Each head was supposed to be adept at something. One head at music, one head at statecraft, another head at warcraft, another head at astrology, another head for astronomy. This is what it was. So think of that and think of this multi-headed attention. They kind of resonate. It's the same way of thinking that each head is worried about one particular aspect of these words. At one head, we can only talk about one aspect, one perspective. We cannot talk about all perspectives using one Q, one K and one V. I may be similar to you under one head, I may be different from you in another head, but similar in some other head. You know, that kind of thing has to exist and does exist. And in order to explore different kinds of similarities and different kinds of differences, they have very intelligently created a multi-headed attention. So each head will have its own Q, each head will have its own K, and each head will have its own V. All of them will be generated obviously from the input, and they obviously are all learned. They are the parameters. So that is a multi-headed attention. Now I'll show you something interesting. Now if you notice something there is an add. Can you see the add there? ADD add. What is it doing? One input is going through the multi-headed attention. Can you see that? Yes. And the other head, other path is going directly. Yes, no? Yes. That's not just for drawing like that. It has a purpose. Now, this is called the residual path. The path which goes like that is classically called the residual connection or the residual path. Now that is very important. You know why that is there? Yeah, anybody? You find this in many other networks also. Many other deep learning networks. Many networks have this kind of a bypass. It's not called bypass, it's called the residual path. Why is it there? I just want to look for the phrase. It solves one problem. I should get 2 answers by now. Why is it there? Are you not interested in deep learning? It is there in many, many places. This bypass. Okay. See, imagine that bypass is not there. That residual path is not there. See, this is a deep learning network at the end of the day. So training will happen, parameters will be there. In fact, Q, K, V, all these are parameters. They are matrices. These matrices have to be learned. That is the whole job of deep learning, right? There are so many matrices at every layer and they will be learned. So, initially we will start with Q, K, V as random values and soon they will start becoming smarter. There are lots of parameters. So when you say that, how does learning happen in any kind of a network? In even a basic artificial neural network, how does learning happen? We take some values, produce an output, correct? Once we produce an output, obviously initially the output is at variance with the expected output. Then what do? We apply a loss function. Then what do we do with the loss? We take the derivative of the loss. Then what do we do with the derivative of the loss? We backpropagate the derivative of the loss. Remember, they are all derivatives which are backpropagating, right? And why do we do backpropagation of the derivatives? Because using these backpropagated derivatives, we are going to update the weights. Now, I've just narrated what happens. When you do that, when you take the derivative and use it to update, what is the danger? As the network is going to be very, very long. There you are. There is every danger. If you have a very thick network, the gradient will start vanishing. It will become so small. And why is vanishing gradient a problem? Because the gradient is used to change the weight. And if that gradient is so trivially small, then what will happen? The update to the weight will not happen, the network will not learn, and it will be an egg on your face, correct? So if the network ought to learn, the gradient should not disappear, basic truth. So, what do? The gradient is going to come back, right? Come down, the reverse the way we are going. The gradient is going to flow back. The danger now is, how do I avoid vanishing gradient? Any network which is thick will automatically suffer from risk of vanishing gradient. So almost all networks which are mature will have this kind of a path. So the gradient, besides going like this, will also go like this. No, yes. The gradient will come back, or the gradient will be applied. The gradient which is computed after that will be applied directly. Then the gradient won't disappear, because on that route there is nothing, no module, there is no component. So there is no further derivatives. Whatever is the derivative at the top, that derivative gets transferred. The derivative does not go down or explode, both problems. The derivative is unaffected as it goes here, comes here. So at least I'll have some gradient to flow back, and that will protect my updating of the weights. Yes? Because if no gradient flows back, what the hell I am going to update my weights with? I can't. So to avoid a vanishing gradient problem, we always take a residual connection, the residual path. You find this not just in these networks. If you take any mature CNN also, you'll find these paths. Okay? They call, in CNNs, we have a whole category of CNNs which are used everywhere. They are called ResNets. Res stands for residual networks. That same residual network thing is doing the same thing. You'll see if you see the circuit of that network, you'll see there is a bypass path. That bypass path is this. So, we take the input via multi-headed attention. Now you are seeing the input getting converted into, are you able to see three Trishul-like thing? No, yes. What is that? Each input is converted into, each token is converted into three matrices, Q, K, V. That is why the three is not for decorative purpose, it has a meaning. So, now, and also, after every multi-headed attention, we have a normalization, layer normalization also. Now, what is this called? This is called batch normalization. Why is it done? Why do we do batch normalization? This is also a common practice in networks. Is it done just because we like doing it, or does it have a purpose? Yeah? Why do we do batch normalization? Well, very simple answer would have been, I want to stabilize the batch. What is normalization going to do? Subtract the mean and divide by the standard deviation. Now you know standard deviation, no? Basically, you control the range of the values so that inputs don't go too wild, they don't become too small, or they don't become too large. To avoid that and to bring stability throughout the network, it's a very common practice to add normalization layers. In older architectures, normalization used to be only at the beginning. Now normalization is no longer in the beginning. This was the contribution of Andrew Ng. Actually, he is the guy who proposed in the early years, about 7-8 years ago, no more like 10 years ago, that after every convolution layer, max pooling layer, you should have a batch normalization layer. And the results were astounding. From that day, almost all the networks started having a batch normalization layer at various points in the network. So that is the batch normalization layer. So we have the normalization layer, which is called batch normalization layer. Now the batch normalization layer also has two parameters, alpha, beta. Alpha to multiply the mean, or the mean subtracted value, and beta for the deviation. Those are also learned parameters. That means the normalization also is learning, just as the QKV is also learning. There's a whole lot of learning happening. Now we go up. Now we are at the feed forward layer. The feed forward layer, I think I explained last time, has also a very significant goal, objective. What is it? This is the layer which remembers Delhi is the capital of India. It remembers that. It remembers that the native language of Telangana is Telugu. Things like that, which is called factual knowledge assimilated from the whole corpus, that is enshrined during feed forward. So the words are enriched from the corpus, not from the sentence. I hope you are understanding the contrast. In the attention layer, the words are getting enriched from their neighbors. And in the feed forward layer, they are not getting enriched by their neighbors, but they are individually getting enriched by what they stand for. Now, Delhi, wherever it occurs, in whichever sentence it occurs, doesn't lose its status that it's the capital of India, right? So, that is not based on the context. Some of the information is learned from the corpus. And the information that is learned from the corpus is this feed forward layer, is, you can say, captured by training into the feed forward layer. So the feed forward layers adds that, what do you call, the extra meaning of this word, which is not captured by attention. Attention only captures, how am I related to you, how are you related to me, how do you say more things about me, how do I say more things about you? That is attention layer. Feed forward is general knowledge, to put it more simply, it is general knowledge about this word and things like that. Like I gave you that example, the restaurant has a valet and a house doesn't have a valet. So you brought somebody to your house and you gave the keys to somebody, will be a family member. In a restaurant, if you make the sentence and want to continue, you'll give the keys to a valet. Now you don't have valets in houses generally. Okay? So this is what? This is not made out from the context of the sentence. This is knowledge which is gathered over time. So that is what the feed-forward layers do. And then the encoder output now gets fed into the decoder. But I am going to pause here on this. So we are going to first understand the code for the encoder. Yes? We are ready to start? Now we are going to start with each layer. What I recommend is, it's there in your laptop also, I hope. So I would recommend, is that? Okay. I would recommend keep looking at the code if you can't see it here. Just look at the code, it will make sense. Okay. Now we are starting at input embeddings, class input embeddings. Remember, it's the bottommost layer. So we are at that layer. Now I am going to go one by one and try and illustrate how does this happen. So there is three parameters in the constructor. First parameter is the D model. Okay. I'll come to that in a moment. That is basically what should be the size of your hidden representation. I just said that every word in the sentence has to be captured for it into a vector. Now the question remains, how big should the vector be? The bigger the vector, the more informative the vector, and obviously the more expensive the vector from a computational perspective. So how big should the vector be? I have to pass as a parameter, because I have to decide at this stage how much money I have in my pocket. That will decide, rather, how much of compute power I have. That will decide what should be my D model. Okay. The bigger the, typically what are D models? 512. Nowadays the D models are 8192 or that 384. Those are common. This is when this paper was written, a D model used to be about 512 bits was the size, or 512 units was the size of the model, only that much. Obviously, as I said, function of computational power. That is a model. Then the second one is, what is the size of the vocabulary that you are dealing with? Now obviously, the vocabulary size, if you are dealing with English, is pretty huge. I don't know how many words are there in the English language, but you don't need to worry about all words. At least the common words, they should be there. So that depends on what vocabulary you are going to design for your transformer. What should be the language size of your transformer? So those are the first two parameters. Now you use that to set the thing, and you now instantiate the D model. That's just a parameter. You instantiate the vocab size. The line below that is important. Now you create an embedding. That is, you create an embedding object. You have not done embedding yet. We are still in the constructor, so we are not doing anything yet. We're just creating the embedding object, and just see the parameters to the embedding object. What are they? There are only two: vocabulary size and model. That is enough for the embedding. So given any word, given any sentence, chopping into words and converting it, it needs, why does it need vocabulary size? Because that will give the range of the tokens. And why does it need a model? It needs a model because that vocabulary has to be finally converted into one word or one token or one vector of D model size. So imagine every word has to become a 512 vector which represents everything about that word in terms of its meaning, not its relation to others. All that is not captured, but only what that word means in general. So the vector representing that word is of D model size that your embedding should know. That is, it has to generate this much vector, this size vector. Okay. So I have defined the embedding, and now we perform the first activity, which is the forward of the input embeddings layer. Can you come down? It's only one line. So see what the forward does. it takes X. X is what? No, X is the whole sentence. Sorry. X is the whole sentence. Yes, no? Yes. All transformers take one sentence as one shot. I think I talked about last time. It's all parallel processing. So that's the reason they are so fast. If you compare them with that RNN, LSTM or whatever, they go word by word. They are very slow. He is capable of huge parallelism. So what is he doing? He is doing self.embedding X. He is doing the embedding using the embedding which we have just created, converts it into an embedded form, and then this second term is not so important. It multiplies it with the square root of D model size. That is just a normalization effect, because at a later part I divide it by square root of D model. So it's upgrading it to look like a slightly bigger value. So it's just normalizing. This we do for maths. It's not for its semantic or syntactic purpose. It is not a conceptual thing also. It's just a normalization thing which most maths people and computer science people are used to. They do it often. So that is a square root of D model. We're just multiplying it. So we have now got the embedding. So the job of the input layer is only to perform the embedding on X. So at the end of input layer, I'll have the embedded version of X, which will be what? A sequence of tokens, sequence of words converted into a sequence of tokens. I am using the word token and vector synonymously. So there will be a vector for every word, which represents the meaning, the semantic of that word. That's it. It has nothing else. Okay. So that is where we are. What is the next layer after this? You remember the picture? After input embedding, converting it into tokens, what do? I do positional encoding. Now, positional encoding is a very funny way of capturing position. So we'll go there, understand positional encoding. Okay. Now, before we proceed, now this is how positional encoding happens. But before that, let me illustrate what it means. So I'll first understand what are the parameters. Pos means position in the sentence. Correct? Every word has a position in the sentence. First position, second position, third position. You understand that? That is pos. I have to encode that. And there is I. I represents the index in the vector. This will require a little explanation. See, I said the vector is 512. Agreed? So each position in the vector, each index in the vector also captures the flavor of the position, or rather a flavor of the position seeps into every position of the vector. Now if you think the vector is 512 bits, imagine a vector is 512 bits. Each bit of that vector captures something about that position. Yes? No? Yes. Okay. Now you'll ask why? Why should every vector bit capture about the position? Reason is, at a later point I told you about multi-headed attention, where we are going to split this vector under multiple heads and do query key value attention analysis on each group of bits. You are with me? Yes, sir. So each group of bits or each bit has to carry that I am a bit about a vector. That vector is at this position in the sentence. Once again, there is a bit in the vector is in the sentence. I have to capture information in that bit about position of this sentence and which bit I am. So I represents the bit position. So what they do is the even bits they encode using a separate function, and odd bits they encode using another function and then put it together. I'll repeat. Even bits we use a different function. Odd bits in that vector use a different function to capture position. So two things and two thoughts are there here. First thought is every bit in that vector must be given a flavor of the position. First point. Second point, odd positions are given a different flavor and even positions are given a different flavor. And this flavor is brought using the sine and the cosine functions. Now you'll ask, what is so special about sine and cosine? I'll tell you. The beauty about sine and cosine are both are periodic functions. Their periodicity is very valuable. The periodicity reveals distance. If I am separated so much from you in periodicity, I know how far are you from me. Okay. You know basic trigonometry, I am sure. See, pi by 3 and pi by 6 have the same difference between each other as pi by 3 plus 2 pi and pi by 6 plus 2 pi when sines are taken. Sine of 2 pi plus pi by 3 is same as pi by 3. Same thing works with cosine. Logic is the same. So, what does it lead to? What does it mean? So, by using these periodic functions and using this I and pos, each bit of every vector is able to make out where am I in the sentence, some flavor of that. And if you show me two such words and two such bits of two such words, they will tell me also how far are they away from each other. Okay, if you are not getting this, park this thought. You will get it at some point. It requires a little more jump in abstraction before you get there, but just believe me this, believe me here, that the periodicity of the sine and cosine function enables me to not only capture the absolute position that is anyway coming through pos, but also enables me to capture the distance between two words because of the periodicity of sine 2 pi, of sine and cosine. Okay? So just keep it like that, okay? Because nowadays, for two reasons, it will take a little while to get it. Spend some time with ChatGPT, that's what I do normally, and understand what the logic is. But this is the essence, what I am saying. So, what do we do? Now, the position encoding for a given position goes like this. So, we have, I compute the position encoding of every bit at a particular position like this. Sine of pos by 10,000 to the power of 2i divided by d model. The function is incidental. But just understand that that function somehow is able to capture the absolute position in pos, and using the periodicity, it is able to capture the relative position between the words also. Just keep that with you and we are fine. So what will I do now? I'll create the positional encoding for the whole vector, for the whole sentence, sequence. For every vector, I will create the positional encoding. Okay. I'll pause here and ask you this. if you take one sentence and take another sentence, will the positional encoding change from sentence to sentence? Just the positional encoding. Embedding obviously will change. Obviously, you are talking of a different word. But I am just asking, will the positional encoding from one sentence to the next sentence change? No. It won't change. Why it won't change? Because it is dependent whether I am a word in sentence 1 or I am a word in sentence 2. If I am the first word, in the sentence 1 and I am the first word in the sentence 2, my positional encoding will be the same. Yes, because it's all relative to the sentence. My positional encoding is not going to change based on which word I am. It depends only on my position and how I am close to other positions. That's all. It is not based on which word I am. Yes? Okay. Now, that is the beauty of positional encoding. So, the positional encoding layer is a layer which doesn't learn because it doesn't change. So, from a learning point of view, from a gradients point of view, from backward propagation point of view, the positional encoding layer just doesn't care. It can be done only once. The computation of this can be done only once and kept. And every time you have a new sentence, new bunch of words, add the same positional encoding to every word, to all the words in that sentence, same positional encoding you have to add. It doesn't have to be redone for every input. Have you bought that?
Yes, sir.
That's a very good optimization, and most of the time during training we ask the training system, don't touch this. This is not going to change. Why do you want to do any training? Saves a lot of effort. Okay, now we will look at the code for this. Yeah. Now, if you look at it carefully, this is how the positional encoding is done. The parameters to the constructor are the D model size, the vector size, 512 or whatever. Then the sequence length, there is a maximum sequence length to the sentence, whatever it may be, maybe 200 words. You want to put a limit to it, you can put a limit. Then there is a dropout. This is optional. Now, do you know what is dropout? Yeah. Randomly, we just disable some of the bits in the vectors so that the same bits do not influence the learning. Common strategy which we use in deep learning, just ask some of the bits to be silent. You don't contribute. By not asking those bits to contribute, you are not allowing those bits to become indispensable. Otherwise, sometimes in training what happens, the weights which you apply to certain bits or certain positions start dominating the learning. And if those words don't come or those words are not there, then the sentence doesn't get translated. So we don't want that. That's a common problem. That's why we have dropout. Typically, by default, dropout is 10%. 10% of all bits in every vector are made 0. Basically, they have no effect. By doing that, we are ensuring that all bits get importance. This is a common technique. Okay? Okay. Now, we are making it, we are defined the positional encoding matrix, which is of dimension, sequence length, whichever way you want to look at it, sequence length, and each is of D model size. So, if sequence length is 200, it is 200 by 512. Yes? Because You will have 200 words and 512 is the size of each word vector, correct? So that is how 200 into 512. Okay, so you create that zeros. Now you apply the division term. Okay, you just say this is the equation. Okay, I'll just go up. So if you look at this and you have looked at that equation, it is that application of the sine and cosine. Remember I told you odd bits will have sine. No, even bits will have sine, odd bits will have cosine, could be any way. So that is a 0 to 2, 1 with a gap of 2. So that is the sine, that is the cosine. Then there is a division term which captures the I and the position. So now coming down, P dot unsqueeze 0 adds an extra dimension for batch processing. We keep doing this for batch because every sentence occurs in a batch. So we are adding the batch dimension. And then once the P matrix is built, P is a matrix, the positional encoding matrix. P stands for positional encoding matrix. Once that matrix is built, what do? I know this is not going to be trained. I store it permanently in a register. So I buffer it rather. So you see that line self.register buffer P, because I don't want it to be considered as a model parameter and it's not going to be trained, it's going to be fixed, so I fix it. Okay. So that is it. Now the actual act of positional encoding, if you notice X is what? My embedded input, to which I have to add positional encoding. Positional encoding is added to every vector. Okay. So how do I add? I just do a plus. So if you notice the code, it is, see that code in the forward, X is equal to X plus self.p and see the dimensions. We are adding that whole thing. X shape 1 means only how wide X is, that many time only it has to be added. P that way is a big matrix for 200, but currently the sentence may have only 150. So I want to only apply 150. So that's why you see there X is equal to X plus self.p, all the rows, that is batch. Sequence length I restrict it to X dot shape 1 and also obviously the rest of the vector. Requires grad false. This is important. Requires grad false means it does not require a gradient, backward gradient computation. So I marked it as false. That means this is never going to change. This is not going to learn. This is permanent. Okay. Then lastly, I apply a dropout and that dropout then does self.dropout X and it produces that. That's the dropout. So basically, so far what have we done? We have taken the input, we have embedded it, converted it into vectors. To that vector, I have added the impact of position called using the positional encoding, and on that I have done a dropout function to ensure that some percentage of the bits are off so that they don't unduly influence. That's it. So that is called what we call positional embedding. Okay. So we have done embedding and now we have moved in the diagram, if you remember, from embedding to positional embedding. We have moved one layer up. Now we come to the main stuff, which is the attention layers. Now before that there is a code for add and norm, which is actually later, but the code is earlier. So I think we will do that in that sequence only. We'll do that afterwards. Let's do feed forward attention first. Okay. Now I'm going to focus on how does the multi-headed attention work. Okay. What do we have? I'm just repeating, we have a sentence. So visualize a sentence in your mind which are given to the LLM. Sentence has been broken down into vectors. These vectors have the meaning and some understanding of the position. That's it. They don't know about each other. They know who they are and where they are in the sentence. How they are relevant to that sentence or how the other words connect with them is not yet known. Now we will tell them about the rest of the words. Now they will turn their attention towards the rest of the sentence and will enable them to absorb information about the rest of the sentence into their individual vectors. What is the idea? The idea is to enrich each guy's vector with meaning from his neighbors with which he is occurring, the other words in the sentence. Okay, now going down, now we are getting the input. Can you visualize the input in your mind? Sentence, vectors for every word. Each vector knows its meaning, individual meaning, and knows its position. So far we are there. Now, you notice the Trishul, which was there in the picture now on the left. What we have is, we have three matrices, Q, K, V. Their dimensions are D model by D model. In our example, 512 by 512. So let's talk a little about dimensions which are coming now. Batch is one dimension. Sequence length or sequence word in the sequence, that is another dimension. And each individual vector, that is a D model. So at this stage, the input dimension is batch into S, S being the sequence length, into D, D for D model. Everybody agrees with me? That is the input dimension that I am dealing with. B is for batch, we do deal data in batch, batch of sentences. Sentence is sequence, S. Which sentence, right? And in each sentence, there are words. So D model for every word. So that is our dimension so far. So our input is in that dimension. Q is in which dimension? D model by D model. These are initially random matrices, obviously. Like in any learning problem, we don't know what weights to give in Q, so they are all random. So they are of dimension D model by D model. So the output of this is, we have the QKV, and the QKV gets multiplied. The same input goes as QKV. Initially, input itself becomes, first time, input itself becomes Q, K and V. Okay. Then what do we have? We have, so each is done like that. Now first we take it through a weight which is WQ, WK, WV. Now this is what I was saying is random. WQ, all are D model by D model. So these are all random weights which multiply the input only. So let's just get the dimensions right. My input is B into S into D model. That is initially treated as QKV, all, for the first layer. Then we are multiplying with weights for Q, weights for K and weights for V, which are random weights in the beginning. They will learn and they will become exact over time. Those are the billion parameters and all, they are all coming from here. Okay? So they will soon fine tune or tune. When I get the output, what is the dimension of my output? B into S into D model again. Because if I multiply B, S into D, by D into D, what will I get? I'll get BSD. No, yes. Correct? So it is BSD at the moment. Okay, now let's keep B and S separately. Let's look at only D now. That is, we are looking at each word. Okay? We are looking at only D. Focus your attention only on D. Now what happens is, each D is split. Each D is a vector, which signifies the position and meaning of that word. That's why I said each bit has to capture the position and the meaning. So I take this D and vertically chop it into number of heads. So if the number of heads is 4, like is there in this picture, I will chop up 512 into 4 chunks of 128 each. Yes? Now I will have a, if you notice, I'll have a Q which is split, K which is split, and V which is split. Can you see that? It's visible, na? Q is split into 4. 4 because I am using 4 heads. I told you nowadays nobody uses 4 heads. Nowadays I think ChatGPT 4 uses 384 heads. So it chops into 384 pieces, but their original size is also pretty big. Okay? They don't deal with 512. They deal with 16K vectors and then chop it. Okay, so it's all of a different scale, but the basic thing only, same stuff. So it's chopped. Now, once it is chopped, then under each head, now can you see it vertically? Each head has its Q, K, and V. How did I arrive at the Q, K, V? By chopping. This is how I arrived at. I got the original Q bar, K bar, V bar, chopped it up into 4. Now, the attention works not across Q, K, V, but across only each head. So under each head, I do what? I do Q into K transpose into V divided by root of D model. I've already multiplied, if you remember, root of D model. So that gets kind of cancelled here. That's only giving some semblance of values. So now I have Q, K, V under each head. Now think of each head in the Dashanand kind of example, where each head looks at a different aspect of that word and different connections between the words. So QKV is what? Each word will have a Q, a K and a V, and I'll connect with all other words. Okay. So this exchange will happen and the attention mechanism will now work like this. Q, K, T, V by root dk, but actually it is working on Q into that matrix and all that. This is the actual attention mechanism. And there is a, in between, we also do a softmax operation. Reason is we want to convert everything into smaller numbers. You know what softmax does, right? It takes a set of values and converts them such a way that all the values are normalized to 1. I mean, the total sum of the values should become 1. This is to do probabilities. And if you notice now, here everything becomes clear. See, I have a sequence because there are so many words. Yes, no? You see the sequence dimension down. See, the attention is between what? Between all the words in that sentence or all the words in that sequence. How do I do that? Every word I chop into 4 parts and do the attention mechanism between this chopped portion here, this chopped portion here, and this chop portion of the all other words. All other words of where? Of that sentence. See, each word in the sentence is split four parts, and between each part of one word and one part of, and the same part of another word, I do the attention mechanism. The attention mechanism is done headwise, not across heads, because each head is one kind of attention. We don't mix up. Each head captures one essence or one perspective. So now all the heads, at the end we have each head, sequence of heads, and the size of each head is now called decay. Decay means that portion, like in the example that I said, 128, that will be decay. Following? Yes. So each decay will be 128. Then, now I have chopped up, I have made them interact with each other. Now what do? I now bring them together. I am done with the attention mechanism of this group of words in this sentence. I am just in one layer. I have done the attention mechanism between all the words in that sentence under all heads. Now I concatenate all the heads across the sequence. So I have that H which you see there. Then, before generating the output, I have one more head which looks at the sentence as a whole. So far we looked at different aspects of a single word. This query, key, value, they all were dealing with, were different for each word. Each word has its own query, not each word, each portion of the word has its own Q, K and V. So we dealt with that. And now we apply another weighting for the whole sentence, which we have not done yet. So that is what you see the WO, which is applied to the whole sentence. Once you do that, you get the output, which is called the MHA output or multi-headed attention output. This is what is called the famous MHA. This was the one, if you will, the whole LLM story and its success is because of this one slide. This was new. People had not done this before. This question of passing attention, having multiple kinds of attention, different heads, putting it together, treating the sentence as a whole, nobody had done it before. This is where this paper went ahead and became a seminal paper. So, in essence, this is where the story of this, if somebody wouldn't have figured this out, you and I wouldn't have ChatGPT. This was the one which made ChatGPT happen. And you will say, what took so long? Why didn't somebody think of it earlier? That alone was not the problem. The problem was GPU power also. This required training, this required so much of compute power, all of that. So, obviously, it took mankind 2000 years to get here, overall. But from here, the leap is fantastic. Now we are moving at a completely different pace. This made the change. So simple. So it's imperative that all of you as computer science students should know this. Each one of you will know it at a different level of comfort, different level of depth, different perspective, but you should all know what is happening at a core. Okay. So after this, we'll see the code of multi-headed attention. This is the multi-headed attention. I suggest you look at the code first. Give yourself about 5 minutes time look at the code, then we'll walk through the code together. So I'll pause for 5 minutes. You look at the code, it's there with you on laptop or on the phone. Just glance at the code. Which code are we seeing? MHA, multi-headed attention block. That is a code I want you to see. Yeah, so we have the constructor init. Init takes as usual those parameters, D-model, H, heads, and whatever the dropout percentage if you want. It initializes the D-model and the head. The only assertion there is useful. What is that assertion for? The D-model divided by heads. The heads should divide the D-model. Otherwise, obviously, you can't make them into chunks. So that's the check it is doing. Now starts the attention mechanism. So dk is equal to D-model divided by H. I told you dk becomes the chunk, the portion. Because now D-model is 512, dk is 128 if the number of heads is 4. Okay, now what happens? See each layer. Now we have those 4, WQ, K, V and O. O gets applied later. So let's not come to O immediately. Q, K, V are all D-model by D-model. As I said, they are all D-model by D-model matrices, and they are of initially random weights, which will be learned through the gradient, through the application of the back propagation through the network. They will be learned. So now K, Q, V weights are fixed, weights are there, random weights are there, and then we are also creating a dropout object which we'll need if we need it. Okay, now we go to the actual attention mechanism. Now if you notice, attention mechanism takes several parameters. Let's understand those parameters. So the parameters attention takes are the query, the key, the value. I'll explain that in a moment. And then the mask. See, sometimes what happens, not in the input so much, but in the output, we don't want the transformer to look at the entire sentence. Here it is not used, but in some transformers, we look at only part of the sentence. So the mask helps us select only part of the sentence to look at. So that is why mask is there. For the present example or present discussion, you can forget about mask, that mask. Dropout is dropout if you want to create a dropout. Okay, now let's see how it starts. Okay, now dk you can obtain there also, or it is, sorry, I didn't make a very important point. Initially, that is for the first layer, first MHA block, the input itself acts as the QKV. All three come from input, first time. You saw that threshold going up?
Yes, sir.
Yes, no?
Yes, sir.
So for the first layer, after positional encoding, input acts as initial Q, KV without weights, obviously. Okay, so I ask the input. Now, what is the dimension of input? Batch into S into D model. Okay. Now, here the last dimension of query key value is dk. Actually, we will treat it as dk for the time being. Okay. Now comes the point of query. Okay. Now see that attention scores and think about why that Q query and key transpose is given by that. So now the query's dimension are sentence, or rather I should say B, S, DK. That is query. Key is also B, S, DK. I am repeating. Guys, this is important to understand. The dimension of query, shape of query is B. B standing for batch, because you take a batch of sentences. S, which sentence? S. DK, which chunk? Remember, we had originally D model. We split that into 4. So that's how DK came about. So Q is of dimension at this stage, before doing attention, is of the dimension B, S, DK. And K is also of dimension B, S, DK. Can I multiply these two together? Obviously not. I can't multiply B, S, DK with B, S, DK. So what does our equation say? Take the transpose of K. So reverse the last two dimensions of K. So what are the dimensions of K now? B, DK, S. No? I'm losing you. No, you have to think with me. See, originally, what was Q? B, S, DK. K was also B, S, DK. All are similar. I can't multiply them. Equation also recognizes that. It says Q, K transpose. So I have to transpose K. What transpose K? How? Last two dimensions. So now after transposing, K becomes what? B, DK, S. DK means that small chunk. Can that be multiplied with B, S, DK? Yes. Yes. So if I multiply B, S, DK with B, DK, S, what will I get? B, DK, DK. Okay, think of it. Anyway, that's not so important as long as you figure out how to do it. Now, I also divide it by the square root of DK. I told you why. Because of the earlier multiplication. I got the attention scores. Now, let's skip the masking because it's not done. Now, I have got the attention scores. Now, it's DK or whatever. Now, I have to apply some kind of normalization to it. I apply a softmax so that the values are all brought below 1. And the aggregate of the values is 1. Okay? Not only are they brought below 1, the aggregate of all values is below 1. Is together 1. Then I apply the attention scores, drop out. If I want to remove some of them, no need. Finally, I multiply attention scores with value, with the value. And I will get at the end BS DK again. Because I would have got BS DK so far, and I multiply that with DK into DK, I will get again BS DK, which is what I wanted. So what have I done? I have performed this multi-headed attention by breaking into heads. Now they are still DK, please. I have to still concatenate. I have not done the multi-headed attention yet. They are still BS DK. I have to put them together. I have to do a concat. Okay. Somewhere below, this is just the setup. So somewhere below, you will see the application. That is, weight is getting applied to Q, K is applied weight, all of that. And then the various views are getting done, the transpose is being done. And I will now take your attention to the last line, last but one line. Now, obtaining the H matrix, x dot transpose 1, 2. Doesn't matter whether you don't get the whole thing, you can try out dimensions. Finally, what is the dimension I'll get? Look at that line, x dot shape 0, that is B. Yes? Then minus 1, I don't care. Let it figure out. Okay? Then, are you seeing that last parameter? Self dot h into self dot decay, where I am bringing all the 4 heads together and now transforming into D model. So far it was all decay pieces. Now I am making it a D model piece. Now I am not getting into individual working, because that you can do. As long as you get the grip on the whole thing, that's more important. So at the end, I get BSD model, not decay. I have combined them together at the end. I have taken each head and done. And finally, I am not yet done with the last line, return self dot WO. Remember I showed you another output matrix which takes the whole sentence as a whole and applies it to the whole thing. You see that? To the whole X it is applying, whole batch, to the BSD, D model. It's applying to the whole thing. That is one output transformation for looking at the whole batch as a whole. Okay. So this is what is called the MHA mechanism. Are you with me? Yes. Difficult? Not so difficult. This is the MHA. So we have seen input embedding, we have seen positional embedding, we have seen MHA mechanism. Now, there is two things. One is, remember I showed you a residual path and a normalization. Remember there was an add and norm. I showed you in the picture. Now, add and norm has 3 parts. One is normalization, second is residual, and third is addition. I mean, you can say 2 parts. So, how does that happen? Okay. So, we have to understand how layer normalization is done, batch normalization, and how the residual connection is done. So, if you see the code, now go to the code for layer normalization. Again, I will give you 2 minutes. Look at that code for layer normalization. W underscore O. See, what happens often is you are passing a batch of sentences. It's applying to the whole batch. When you are applying, taking the whole batch, taking a whole pool of sentences, always we have to see 2 things. What logic is there for the sentence, and these batch as a whole or this group of sentences as a whole, does it reveal anything? So that is W. See, the purport of putting these words individually have become smart, but we have not ever looked at the sentence as a whole, or especially if you have entered, let's say 4 or 5 lines, the correlation between that lines also is not captured. So something has to be learnable to capture that. I think it is with that thought that they put W. Otherwise you are done capturing the attention mechanism, sentence level. Okay, now see there are, okay, I think I can go directly to forward. And show you the equation. The last line is important. If you understand the last line, you understand what is happening there. There is an alpha, which is a parameter, which is used for normalization. So alpha into x minus mean, this is a normalization procedure. How do you normalize things? You take any x, you subtract the mean, multiply that with an alpha, then divide it by not just the standard deviation. Okay, why do you need that EPS? Yeah, why? Comes 0, correct. See, why do you have that EPS in the denominator is, if the standard deviation becomes 0, then you have a division by 0 issue. To avoid, this is also very common. So to avoid the division by 0 issue, you add an epsilon, small value. Okay, so that's the last equation. Now, the magic of this is, if you visualize this is regular normalization. You have alpha into x minus mean divided by standard deviation plus epsilon. Worldwide, this formula is used, right, for normalization. What is interesting here is the alpha and the bias, that added term, both are learnable parameters. See, in every transformer network, you have to watch carefully what are learnable parameters, because that means they are controlled by the gradient. They will change and they will learn. They are not fixed. Nobody is saying like learning rate, LR is equal to 0.01. Those are hyperparameters. Alpha and bias here are not hyperparameters. They are learnable parameters. They are going to learn. They are going to change. Their gradient is going to be taken and their values are going to change. So that is a very interesting thing which they have done. If you see classic normalization, they will work with a fixed alpha and a fixed bias. They will not make it variable. Here, by making them as parameters, they are subject to gradient. And because they are subject to gradient, they will change and learn. You have to understand the difference. When do I make something a hyperparameter and leave something as a parameter? I'll make a hyperparameter when I don't want it to change during training. And I'll make it a parameter if I want it to change. So the designers of this algorithm wanted it to change. So that's why they did this. So if you notice that alpha, if you look at the top, alpha is a parameter which is initialized to ones, but it's going to change. And bias is also a parameter which is initialized to 0, but it will change. The initial values are given here, but they will undergo transformation. And then we are using them, we are computing the mean, we are computing the standard deviation from x, and then applying that normalization. This is called normalization. Yes? Now, we have figured out embedding, positional encoding, MHA, normalization. What are we left? Add, which is called residual connection. That is called a residual connection, where you do it to avoid the vanishing gradient. So now we are not yet feed forward. Now go to the residual. You will see the residual connection. Look at this code. Again, I'll wait 2 minutes. Look at that code for residual. Residual is nothing but adding that bypass, the bypass that I referred to. But very important. It also applies the dropout at this stage. Dropout, you can forget it. I mean, if it is there, it is there. If it is not, often people don't implement dropout. So that's okay. I have seen, in fact, most code doesn't implement dropout. That's fine. Now, if you notice, what is happening here is they have used a parameter here called sublayer, if you notice in the forward. That is because this add and normalization is applied to MHA layers also and feed forward layers also. So they want to use the same code whether I do add normalization after MHA layer or feed forward layer. If you look at this picture, that add norm, look at the left hand side only, go down a bit. You look at that add norm, it is used with MHA also and it is used with the feed forward also. Yes? So instead of writing two residuals, they have written one residual which does the add norm and takes the layer as a parameter. You see residual both sides, for the feed forward also, for the MHA also. Okay? So that is code reusability. So we go back to residual and see that. It's pretty simple to understand what's happening there. Yeah. So residual initializes itself, forget the dropout. It has initialized the normalization, layer normalization, which we just saw. Now what does it do? It takes it takes a sublayer. Now if you notice, I don't know how many of you will catch, there is a slight variation between the paper and the code here. Can you catch? Sorry? Forget the dropout. Nothing to do with the dropout. A small variation. If you are fast, you will catch. Even if you are slow, you will catch. Between the paper and the code you are seeing, there is a small variation. No, Baba, attention is done. No, this is only the bypass. The attention will come like this. I'll add the bypass. Okay. Anybody? If you look at the picture, उनको picture बताओ. See, normalization is done after the layer. Are you seeing it? Picture. The normalization is there. So, take it, normalize it, then add it. If you see the code ko jao. He is doing what? Taking X, normalizing it first, passing it through that layer, then adding it. No, yes. This is far better than that. That is what people discovered. It is better to normalize and then go to the layer rather than go through that layer and then normalize. So you notice there last line, self.normX, first do normalization, output of that normalization, take it into the layer, whatever, it may be MHA or feed forward, and then add it to the input, X. So sometimes you will see that, these variations. Okay, we are done on that part. So I have shown you residual connection, how does it go? Okay, yeah. So we have by and large all the building blocks of encoder. Okay. Now each encoder, oh sorry, I don't have all the building blocks, sorry, you're right. I have one more block missing, which is very easy, which is called the feed forward. Feed forward is a very trivial layer. I'll show it in a moment. It's very simple. It is basically a fully connected layer. Okay, what we call an FFN or whatever. flat, fully connected layer, it is very simple. What they do, you have batch, sentence, sequence, words. Now, the feed forward layer, remember the job of the feed forward layer is to absorb earlier knowledge. What does it do? It just transforms B, S, D. Now it is D. D means D model. It takes B, S, D model and transforms it into a wider vector space. It's called BSD FF, feed forward. So BSD model gets transformed big into BSDFF. DFF means D feed forward, and then again it is brought back to D model. So it has two layers, two linear layers, one from D model to DFF, the other layer DFF to D model. Now there is a lot of learning of weights, so it's a very simple ANN. Lot of learning of weights in this process. Very simple network. The feed forward. Even a kindergarten guy will understand. So simple. It's just two layers, two linear layers. Go from D model to DFF, go from DFF to D model, back. And in that process, capture all the weights, all the knowledge about the world in general. So that is what is the feed forward block. Very simple. And you also have an activation function, ReLU. So this is the trivial part. If you can see that, two linear layers, linear one from D model to DFF. DFF is almost 4 times the D model. So you open into a big vector space so you can see more, and then again condense it. And again if you see linear 2, it is from DFF to D model. Very simple. But lot of weights are involved here. You can see that, right? So many weights connecting. Remember, in a trivial thing, D model is 512 and 2048, but in big networks it's that much more. It's big models, but simple to design. And well, the lower one actually applies it. So now we are back to BSD model. We went to DFF, came back to D model. Yes? That's it. This is feed forward. This is multi-head attention. Put them together, put normalization between both, and put many such layers together, many such blocks together, and you have the encoder. So I hope you understood. I'll elaborate again. Each encoder consists of input, embedding, positional encoding added, then MHA, then add norm, feed forward, one block. Imagine such blocks stacked one above other. How many of them? ChatGPT 3.5 has 96. ChatGPT 4, I think somewhere I read, has 192. I don't know how many 4.0 has, but it will be some multiple. So imagine 192 such blocks, one over another, stacked. It's very gigantic. Okay. So that is the encoder. Okay. Now, encoder produces what as output? Again, batch, sequence, D model. That's it. Now, depending on the problem you have, you can put a classifier on it, which will only look at the last token, or you can apply a summarizer head on it, which will start summarizing. Depends what use you want to put them. Or in the classic old paper, you take it from here and take the input from here of the decoded, pass it down and decode into another language. If you are designing a vision language transformer, you see so many of them. What will you do? Very simple. Okay, maybe, is that done? Done. Okay, now I'll just stop in 2 minutes. Now if you look at this picture, even this picture is fine. Scroll up. See, from this transformer, DALI for example, if you are doing DALI, what will you do? You'll have a CNN generating tokens from the picture. You'll take those tokens, you'll have the text tokens, you have to train them together. So you'll bring the visual tokens from a CNN, you'll bring the text tokens from the English while training, try to bring them together so that the variation between the visual tokens and the text tokens start shrinking. And anyway, maybe I'll describe it one day. Actually, we can go through it also. But I think we'll pause for today.